Welcome to problem solving session for computational commutative algebra. I am Siddhi Balgambure from IIT Gandhinagar, and today we will discuss problems related to syllabus from week 5, that is problems related to associated prime, primary decomposition, support of a module, and prime avoidance lemma. So let us start with first question. So let G be a finite abelian group. Then we have to check whether the following statement is true or false. That is, 0 is an associated prime ideal of G. So when we are talking about finite abelian group and 0 is an associated prime of ideal G. So to talk about this, associated prime concept, we look at a group as Z module. Okay, so every abelian group or every abelian group is module over Z. Okay, so first of all, let us see the definition of associated prime. So let M be an R module, and we say that a prime ideal P is associated to M, or P is an associated prime ideal of M if P is annihilator of X over some R, so for some X in M. So when P is annihilator for some element X in M. So what is annihilator? It is all those R. So annihilator over R. So we are looking at annihilators of X in R. So all those R in R such that R into X. So this is module multiplication is 0. Okay, and this 0 is 0 in M. Okay, so this is the definition of an associated prime. So, and how we will be looking at Z, the given group G as a Z module. So the module multiplication will be defined like this. So this module multiplication is like this. So abelian group condition is anyway satisfied. So we have to give now scalar multiplication for it to have a Z module structure. Okay, so it is n comma x, so n in Z, x in G, and it goes to n into x. So what does this mean? It is x plus x n times in G. This G is group G comma plus. Okay, any doubt here? How the multiplication is and how this G is looked at as Z module in Z, as a Z module. And this 0 is an associated prime. When they say that, it means that this 0 ideal. So in Z, 0 is a prime ideal since Z is an integral domain. So we just want to check whether this Z is annihilator of some element X or not. And G is given to be abelian group. So any cases now that all the definitions are clear in the question? Can we have an element such that it is annihilated by only 0? So note that when we say that 0 is annihilator of some x over z, it means that the ideal 0 contains only element 0. So 0 is it means 0 into x is 0. That's it. This 0 is in z. This 0 is in g. I mean, let me write here 0g, 0z. And no element x, sorry, n in z non-zero such that n into x is 0. Okay, is this clear? Like this is happening when we are saying that 0 is associated prime for some element. Because this is collection of all such R. So if there exists some other element which annihilate this x, if this happens, is this clear? So this is happening. So can we say that this is true, that 0 is associated prime? Can you give me an element for which only 0 is annihilated, that it is annihilated by only 0? And note that we are in finite group. So any guess that whether this will be true or false? So note that this is actually false, because note that since we are in a finite abelian group, for all x in G, there exists some nx in G such that this nx, this x power nx or nx into x is 0 in G, right? When I write this, I mean, my group, okay, my group is under addition. So this nx into z is like not even nx we need. Even the since G is finite, so cardinality of G will be some n. And for this n, x plus x n times will always give me this 0 of a group. So this implies that for any given x, this n belongs to annihilator of x, right? And this is non-zero. So therefore, 0 cannot be an associated prime of G. Is this clear? And in fact, if we want to, I mean, look at it in even, I mean, this is very general. When I say that I'm writing this n order of group, so this n actually for given element, this order of element x in group G will actually generate annihilator of this x. I hope you understand this, what I'm trying to say here. Is this clear? So this is actually false. So if I want to have 0 to be associated prime ideal of G, then G should have at least element, I mean, a copy of Z must be inside G. When I say this, I mean there must be at least one element such that for which the order is infinite and something of that sort. Is this clear? Okay. Okay. Cool. So we will move to now the next question. Please feel free to ask if you have still have any doubts, or I will move to next question. So the second question is that now let R be this quotient ring x comma y quotiented by x square comma xy. Okay, and now we have to pick the correct statement. Such that they are saying that y belongs to associated prime, means set of. So this means set of all associated primes of R. When I say associated primes, I mean associated prime ideals of R. Okay, and next statement is that x plus y is an associated prime of R. Third one is x comma y is an associated prime of R, and fourth one is none of the above. So any guesses here? What will be? So we know what associated prime is. It has to be any letter of some element. Okay. So any guesses? Yes. Ideal generated by X is an annihilator because it annihilates the element X and also element Y. So that is there. So X, can you give me what is X is annihilator of X, right? No, it's not annihilator of X, it's annihilator of Y. Because annihilator of X actually is, is what? So therefore X belongs to associated primes of R. So is Y is Y associated prime of R? Any guesses whether Y? So think of this, but meanwhile, is, I mean, I'm saying that Y is annihilator of some element here. Can you guess this element, or there does not exist such element for which Y is an associated prime? So we have to guess from these four or these three. So is Y associated prime? So you are saying Y is annihilator of X, but actually annihilator of X is both X and Y, because X into X, because this is what? This is all those R in R such that X into R is 0. So X into X is 0 bar because of this X square here. And also X into Y is also 0 bar in my ring R. So annihilator of X is actually ideal generated by X and Y. And it is not only just, I mean, it is not only generated by Y, because it is collection of all the elements which annihilate X. Okay, so this is not true actually. Not true. Is this clear? I mean, why this annihilator of X is not Y? It's not Y. Okay. So annihilator of X is indeed, I mean, this ideal generated by X and Y. So therefore, this is not associated prime. And this, we got that is associated prime. And what about this? I mean, yeah. What about X plus Y? What can you say about this ideal X plus Y? Can this be annihilator of any element? No, okay. I mean, when we talk about associated primes, um, for a monomial ideals, the associated primes are also monomial ideals. So this here x square comma xy is a monomial ideal. This x plus y can not be its associated prime. Okay. So please understand that. So this is the only associated prime. This is not the only associated prime. I mean, of course, from the options, x comma y is the only associated prime. But in general, as Subhadeep also pointed out, that x ideal generated by x itself is also associated prime of this ideal. So let me write. So associated primes of R, yes, is ideal generated by x and ideal generated by xy. Is this clear? When I write this, I mean this, they are in quotient rings and so on. And this therefore belongs to. Okay, so I don't. So let us see how this is calculated in Macaulay 2. So let us define this. Is this screen shared? Okay. Okay, so this is ideal x comma y quotienting with ideal x square comma x star y. Okay, this is our ideal. I mean, this is our ring, and this is associated times s, and this gives me these two ideals x comma y comma x. So y comma x is I mean as ideal generated by x comma y. So these are the only associated primes of x and y. Is this clear? I mean, how associated primes are calculated. So this is the code which we need to use, and you can just change this ring to just yq x star yq, and check it will be still the same. But now if I don't have this, it's just one associated prime, y index. Okay, so you can try this and check for associated primes of different ring. And associated prime also works on ideal. Okay, so if you define this ring, then just define this ideal I is equal to any. And I'm just doing this so that you know that the associated primes is applied on ideals or as on a quotient ring. So see, these are two associated primes of this ideal I. So any doubts in how these functions are working? Okay, so associated primes is a command for in Macaulay 2 to calculate associated primes of given a quotient ring or ideal. Okay, so it means okay. So I hope there is no doubt in that. If you have any doubt, please write it in the chat. Otherwise, I will move to next question. Okay, so now third question that we have to check for true or false. And it is that the largest integer such that n less than 100. So this is number 100 such that this ideal generated by this integer n is primary ideal of Z. And they are saying that this n is actually 81. So what they are saying is that we have a ring of integers, and now we are looking at all the ideals generated by integers less than 100. I mean, of course, when I'm writing this, I assume this n to be positive or non-negative, doesn't matter. And they want to say that this n is primary ideal and n is the largest below 100. That's their question. And they are saying that 81 is the largest n such that n is generating a primary ideal in Z. Okay, so let me write the definition of primary ideal. So let n be R modules. So n and m are R modules and n is R submodule of m. And we say that n is primary submodule m if associated primes of m over n is 1. I mean cardinality. So m quotiented by n has only one associated prime. That implies that n is primary submodule. Okay. So, and in a ring, so if we have ring, I mean, this is a definition from Atian MacDonald book, Introduction to Commutative Algebra. And there it said that an ideal, yes, it's false. Yes, can you give me what number is it for which we will have n to be primary ideal and largest below 81? Sorry, below 100. And ideal I is said to be primary if xy belongs to I imply either x belongs to I or y power n belongs to I. Yes. Okay, this is also one quick, if you don't want to go to modules and just want to work in the ring, then this is also a definition which can be used for to check whether the ideals are primary or not. Okay, so yeah, as Subhadeep suggested, he is saying that it is false and 97 is the maximum n such that we have n as a primary ideal of Z. Okay, so let us check. So first of all, let us, Z is Z module. So we are looking at Z as Z module. And we have to find maximum of n such that associated prime of Z mod n is 1. So for ideals, if I is P primary, yeah, so P primary means that the radical, I mean, when associated prime, it has only when ideal is primary, it has only one associated prime, that ideal P. Okay, and that P that so if I is the I is primary ideal which has associated prime P, then I is called pre-primary ideal. Okay, so that's what they mean. If I is a P primary ideal, then any letter of R mod I radical we are taking belongs to associated. Okay, and this is nothing but I itself. Okay, you can check this. The annihilator of R quotient I over R is that ideal I itself. Okay, but when we look at associated primes, oh, so that is the radical of I is P. Okay, so when we look at associated primes, so that annihilator, I mean the annihilator ideal must be prime. Okay, in general, annihilator of an element need not be prime. We can take any element and its annihilator need not be prime. Okay, you can generate such elements, but when that annihilator is forms prime ideal, then that becomes associated prime. Think about it. Okay, so for example, under below 100 we have 9, which is 9 into 11, which is 3 square into 11. So associated prime of Z mod 99 is this 3, 11, because 3 annihilates 3 into 11, and 11 annihilates 3 square. So we have two associated primes in this case, which are 3 and 11. So therefore, this is not primary ideal. So cardinality of associated primes of Z mod 99 over Z is not 1. Therefore, 99 is not primary ideal. And similarly, for 98 also this happens, because 98 is just 2 into 49. So it is 2 into 7 square, and again associated primes. Because here also note that for element 3, the annihilator is 33. Okay, annihilator of element 3 under this ideal is 33. Okay, but this is not prime ideal. Okay, so annihilators, the ideal which are annihilator for some ideals, they need not be prime ideals. But we consider associated prime only the ideals who are annihilator of some element and they are prime. Okay, I hope you understand what I'm trying to say here. And here it is 98. And still we have this 2 and ideal generated by 7. But in case of 97, since 97 is prime ideal, it's only 97, then associated prime of Z mod 97 is in fact this only 90 ideal generated by 97, and that's why, and cardinality here is 1. Therefore 97 is the largest number below 100, such that such that n is primary ideal of Z. Any doubts here? What is happening? And when I said this, that annihilator need not be prime ideal. Is this clear? Uh, okay. So what I said was, in general, this this ideal, this is ideal. Okay, annihilator of some element is always an ideal. Is always an ideal, but it need not be prime. Okay, so therefore this annihilator of X doesn't always belong to associated primes. Okay, so annihilator ideals with how can I say it? If is prime, then is this clear? Because see, under this Z mod 99 which we take, 33 is annihilator of element 3, right? But this is not prime ideal in Z. Therefore, even though this ideal generated by 33 is annihilator for some element, but it's not prime ideal. So we don't consider it as associated prime of ring Z mod 99. Is this clear now? Okay. Uh, so that's it. Is this clear to others also, or is there any doubt? Please feel free to ask. Okay, so let me move to next question if there are no doubts. So question 4. Pick the primary ideal of kxy from the list below. So list is first that x square comma xy. We have to check for primary ideals. So ideals for which associated primes, the set of associated prime contain only one element. This x minus 1 square comma y plus 3. Third one is x comma y, x square plus xy. And any guesses here? Which one of this is associated prime? Sorry, primary ideal. First of all, this x square comma xy is this, right? So associated primes are also radicals of primary components in primary decomposition, if you remember. Okay, so therefore associated primes of this ideal x square comma xy are this x comma xy. So cardinality of set of associated primes for this ideal is 2. So therefore this is definitely not an associated prime. What about this ideal x comma y? Oh, this is not x comma y, this is xy. Product of x and y. This one was first. What about this? So I'm getting rid of obvious which don't feel like associated primes. Okay. So what about this xy? This is ideal generated by X intersection ideal generated by Y. Then again in this case, associated primes of this ideal XY are X and ideal generated by Y. Is this clear? So again, set of, so if you take quotient of this, so Kx comma Y quotiented by this ideal, then this is annihilator of element Y, and this is annihilator of element X. This is annihilator of Y. This is annihilator of X. And fourth one is what? This X square plus XY. This is what? This X into X plus Y. And so I can write this, right? So here this becomes annihilator of X plus Y, and this becomes annihilator of X. Is this clear? What I'm writing? Okay. So now we are left with, so these two are also not associated primes. So let us check for this. So since at least one is correct, so this has to be associated prime. And how to check that then? This ideal x plus 1, x minus 1 square, comma y plus 3. When I take radical of this ideal, it is x minus 1, comma y plus 3. Okay. And we can't also split this ideal in two parts. So associated primes are actually radical of annihilators. Sorry, radicals of elements in primary decomposition. So if I am writing I to be Q1 intersection QR, where each of these are primary ideals, then associated primes of I are radical of this QI, okay, for this R. So when I split this ideals, I should actually ideally take radical of these ideals, X, Y, and so on. But since these are all ideals which are radical ideals, so I have omitted this. But yeah, technically it should be this, and so on. Is it clear? So this we can't write as intersection of two elements. I mean, I can't write this as I1 intersection I2 for two ideals, because if I split them, it becomes the ideal again. I mean, those two becomes, if I try to split this x minus 1, comma y plus 3 and intersection x minus 1, comma y plus 3, this becomes ideal x minus 1, comma y plus 3, which is not equal to this original ideal which we started with. So this is indeed prime ideal with its radical x minus 1 y plus 3. Okay, there is also one statement of associated prime ideal which connects maximal ideals and so on. So this is actually maximal ideal. So if okay, so that's why this x minus 1 square. We will check all this in Macaulay 2. What are the associated primes and radicals of this ideal? is primary ideal. Let me share the screen. Okay, so let us take this. These are ideals in X and Y. And we already checked for I'm directly defining ideal here. Ideal x square comma x star y is this. And the second ideal was x minus 1 square. X minus 1 square comma y plus 3. I hope it doesn't show error for 1 and 3. Let's see. Okay. So associated prime is only this. And so this had two associated primes. The first example, x square comma xy. And the second one has only one associated prime, y plus 3 comma x minus 1. And let us check for the third example. Third one was ideal generated by x into y. And again, it has two associated primes. And the last one was ideal generated by x square plus xy. And it has again these two prime ideals, associated prime ideals, x and x plus y. So that's why the only associated prime, only ideal which contains only one element in the set of associated prime is this ideal. Okay, so that's why this is our primary ideal. All other three examples have at least, or in fact exactly two elements in the set of associated primes. Is this clear? Okay, so if you have any doubt, please let me know about. So let us move to next question now. So question 5 is again true or false. And now they are saying that let R be this polynomial ring Cxyz over complex numbers and I be an ideal generated by polynomials not involving x. When I say polynomial not involving x, it means that I will, let me just finish the question. I will write that down. Then this R quotient I has infinitely many maximal ideals. Okay. So when they say that this I is generated by polynomials not involving x means I is actually contained in this C y comma z, because it does not contain, no element of, so if I is generated by this f1 to fm, then all these fi's are actually, fi are in cyz. It does not contain any element, any monomial term or every term of this these polynomials f1 to fm are from C by Z. They do not contain X. Okay, and so we have to show. So the statement is actually true. Okay, so can you think of this, that how can we have infinitely many maximal ideals here in C, X, Y, Z? So when I say this, that R mod I, or the quotient ring R by I, has infinitely many maximal ideals, it means that I'm saying ideal I is contained in infinitely many maximal ideals, because what are the elements who are maximal ideals in this ring R quotient I, or any given ideal in R quotient I is the ideal which contains I in it, and so on. Okay, so the maximal ideal, when I say the maximal ideal in quotient ring R quotiented by I, all the maximal ideals are maximal ideal in my original ring R, which contain ideal I in it. Okay, so this statement is actually true. So yes, exactly. So that's what we will do. So that's correct actually. R mod I has infinitely many maximal ideals. So what Subhadev is saying is that since I is contained in Y comma Z, so we will look at the maximal ideal which contains this ideal I in C Y comma Z. And that will be some ideal M in YZ. And he's saying that we will just add this X minus A, not add, when we will consider this ideal X minus A, comma this MYZ, and it will be maximal ideal. So, but we have to properly explain this, that why this is true and so on. So, since note that, like how this follows, I mean, it's easy to see, but we have to like put it in proper words. So, okay. So, since I is F1 to Fn, then I is a proper ideal in C, X, Y, Z, and therefore this variety of ideal I is non-empty. Okay, it has some element. Okay, and when this happen, that when we have proper ideal and its variety is non-empty, it happens only when our field over which we are considering the polynomials is algebraically closed. Okay, this doesn't always happen in any given ring. For example, ideal generated by x square plus 1 in Rx. Okay, the variety for this ideal I in R is empty set. But since C is algebraically closed, we get this. Okay, so let A, B, C be in C cube such that A, comma B, comma C is in variety of this ideal I. So this imply what? This Fi of A, B, C is 0 for all I from 1 to n. Okay, just the definition. I'm following the definition of variety and so on. But since Fi belong to belong to C, Y, comma Z, changing this A as suggested by Subhajit, A in the first coordinate of this element ABC will still be an element in variety of this ideal I. Okay, so what we are saying is that f of fi of b comma c is 0 in c y comma z. So, and this fi is when I consider an element of in c x y z, it is still 0 for all a in c. Okay, change any element in the first coordinate and it still gives us 0. Therefore, we have infinitely many points in this variety of I, and this implies therefore there are infinitely many maximal ideals in R mod I. Okay, because corresponding to each that element in variety, this ideal, so for a comma b comma c and v of I, this x minus a, y minus b, z minus c belong to this maximal spec of R mod I. Okay, is this clear? So since we have infinitely many choices for this A here, we can say that there are infinitely many elements in maximal spectrum or maximal ideals of R mod I. Any doubts here? Okay, so since there are no doubts, let me move ahead. So this is question 6. So let R is equal to k x, it's k x y z, and I is equal to x cube comma y cube z square comma x square y. Then the cardinality of mean R mod I is, we have to find it. And what is this mean R mod I? It is minimal associated set of all minimal associated primes of I. So this is mean R mod I is actually subset of associated primes of R mod I, such that this, so for example, yeah, so such that these are smallest with respect to inclusion in the set of associated primes of R mod I. Is this clear? For example, when we were talking about this ideal x square comma xy, for this associated primes of R mod I, so if I take this to be I, is this x comma y. But minimal primes of this R mod I is just this x, because this x is the smallest with respect to inclusion, because this is anyway contained in x comma y. Is this clear? What is the definition of minimal? Here I'm writing minimal with respect to inclusion. Okay, great. So we again are working with this ideal x cube comma y cube z square comma x square y. And we know we already did this last time as well, that when we have monomial ideal, we can split them. So if I have monomial ideal I and f comma g, where GCD f comma g is equal to 1, then I can write this I comma fg as I comma f intersection I comma g. Okay, so I will be using this 3. Okay, so let us check whether it's 3. So Subhadeep suggesting that it has 3 minimal primes. Okay, so let us check. And also, like, if you want to understand even more about this monomial ideals in general, there is a book named Monomial Ideals, if you want to just go through, by Jürgen Herzog and Takayuki Hibi. This book is all about monomial ideals, and the very first chapters gives good information about how the associated primes and primary decomposition of monomial ideal work, and that this book also contains information about Grosvenor basis and everything so on. So you can have a look at this book if you want to just study. I mean, if you want to understand this monomial ideals in depth. Okay, so apart from that, so I will be using this result here to calculate or find this y cube z square comma. Now I'm splitting this. This is intersection of x cube comma y cube z square comma y, right? So since x square divide x cube I will omit x cube, and this becomes x square comma y cube z square intersection. This y divides this element. So I'm omitting this element and I get this new ideal. Okay, and again I have to split. So this is anyway good. It is in the form of primary element or primary ideal. So we can't do anything of it. But now this first element I will split it. X square comma z square intersection x cube comma y. So associated primes are radicals of this x square comma y cube, radical of x square comma z square, comma radical of x cube comma y. What is the radical of this ideal? It is x comma y. For this it is x comma z, and for this is x comma y. So this indeed becomes only x comma y and x comma z, because we are not counting this. Is it clear? So it has only 2 minimal. So now we have associated primes. Associated primes are 2. But what about minimal primes? Are these also minimal? So when we say that something is minimal prime is, yes, exactly. So this is minimal because none of them is contained in other. Okay, so when we talk about minimal, we talk about minimal with respect to inclusion. Since none of them are contained in other, these are the only minimal. I mean, these two becomes the minimal element or minimal associated primes or minimal primes of this ideal R, ideal I or quotienting R mod I. And in general, the minimal primes are like this. So if I, so P is minimal prime of I if for some prime ideal Q, if we have I contained in Q contained in P, this implies that Q is actually P. Okay, so this is quick definition of minimal primes. Okay, just to understand. So, and none of them will be contained. I mean, if you remember, we applied this definition to find minimal primes in last week's session, last week's problem solving session. So you can also look at, I mean, you can try to prove that these are indeed minimal primes using that method. Okay, we started with some ideal Q which was containing, and then considered this and said that since I is contained in Q and XY, so, and we gave proper argument that how this Q will be exactly the ideal X comma Y and X comma Z in, I mean, in those respective examples. So any doubts now? For this, I mean, how to find and what is minimal prime and definition and associated primes, the difference between them and so on. Okay. So moving to next question. Again, true or false. So let x, y, comma, x, z, comma, y, z is an irreducible ideal of k, x, y, z. So is this ideal irreducible? So let me give you the definition of irreducible ideal. So let R be a ring and I be an ideal of R. We say that I is a reducible ideal if there exist R ideals I1, I2 such that I is properly contained in I1 and I is also properly contained in I2, and we have I as intersection of these two ideals. Okay, so why this is necessary is because we can always take I1 to be contained complete. I mean, for example, if I contained in J, then I can always write I as I intersection J, right? So this doesn't really help. That's why we need this. I mean, I is properly contained in both of them and their intersection is giving me the required ideal. Uh, is the definition clear? I mean, there exists some element here which is not an element of I, and similarly there exists some element here which is not an element here. Okay. So we have this xy comma xz comma yz. So can you guess whether this is irreducible ideal or not? Can you give me two ideals which contain both of these ideal? None of them properly contain, I mean, this ideal I is properly contained in both of them, and intersection actually gives me this ideal I. Or do you think that this is irreducible ideal? Yes, exactly. So Subhadeep said that it is xz comma, yeah, x comma. So we will just split as we did. You are saying x comma yz intersection xz comma y. So you are splitting with respect to this element, I guess. Right? You are splitting this first x and y, and you got this because when we split this, we get this x comma xz comma yz intersection y comma xz comma yz, and this actually gives us this because this x divide this element, this y divide this element, and we just get rid of those irredundant elements and we end up getting this. So, and indeed this ideals our original ideal is properly contained in this x and this. Can you give me an element which is in here in ideal x comma yz but not in ideal I, and element which is in xz comma y but not in ideal I? Yes, exactly. So it's clear, right? Because this ideal xy comma xz and yz, it is generated by all 2-degree monomials. Okay, so every polynomial will have degree at least 2 in this ideal I, if I give this ideal I. And we have solved this type of elements with the degree argument. So here we have element x, which is of degree 1. So this definitely x is not contained in I, but x belongs to this ideal, and y belong to this ideal, which is not contained in I. Okay, so this is indeed irreducible ideal. So this is true that it is oh sorry, it is false. This ideal can be reduced, and this is not irreducible ideal. Okay, this is, let me write it, not irreducible ideal. Okay, and we gave the required expression and how it is reduced and so on. Question. Any doubts? I hope, I mean, we have like decomposed many monomial ideals so far, so it's clear. Still, if you have any doubt, please let me know. Okay, so let us move to next question. So let R is equal to this kxyz, and again I is a monomial ideal, x cube y cube x square y square y square z square. Okay, and we have to pick again the correct statements. So let me write them all first, then we will discuss. And meanwhile, whenever I write, please think of it whether this statement is true or not. So they say that x comma y is an associated prime of the ring R mod I, and I mean quotient ring R mod I, and the corresponding xy primary component is x cube y square comma x square y. Okay, so once we have to talk about the primary component, we just go ahead with the primary decomposition of these elements. So these ideals. Okay, and the second one is that xy is associated prime again, and the corresponding primary component corresponding xy primary component is x cube y square. And third one is that x comma y is not an associated prime. And fourth one is that x comma z is an associated prime. And the corresponding xz primary component is x square z square. So this is the question. We are asked to check whether given prime ideal is associated prime. Its corresponding prime xp primary component in primary decomposition. Okay. So how to solve? I mean, we have to anyway do the decomposition of this ideal x cube, y cube, x square, y square, and y square, z square. Again, we have to split. So I'm just splitting as we have been doing so far. Y square intersection x cube, y cube, x square, y square, z square. And this is x cube, y cube. So since x square divide y cube and also x square also divide this element, so we just have x square, y square, x cube, y square intersection. Now we have z square here. Z square does not divide any of these elements, so it stays as it is. And we now split this element x square comma z square intersection x cube comma y cube comma, let me write it below, x cube comma y cube comma y square comma z square. So this is what x cube comma y square intersection. Please let me know if there are any errors in this. Since x square divides x cube, it becomes x square comma y cube comma z square intersection. Again, y square divides y cube, x square, x cube, y square, z square. So these are the three primary components which we have. So what can you say about this? Which of the statements are correct then here? So first check for associated, primary. So radical of this first one, radical of x cube y square is this ideal xy. Radical of x square, if I call them q1, q2, q3. So this is my first associated prime. Y cube z square is this ideal. And third one is x cube y square z square again, and its associated prime is also this. Okay, so that's okay. This, let us call them P2. So it has two associated primes, xy and xyz. So clearly xz is not an associated prime. And xy is indeed associated prime because it is radical of this first component x cube comma y square. So xy is associated prime. So these statements become false. And now they are talking about the xy primary component in the primary decomposition. So this is the primary decomposition, and this is my xy primary component here. So which is x cube comma y square. So the first one is wrong, and that's why the only correct option is this, and this is indeed true that xy is associated prime with the xy primary component x cube y square, and that's it. So any doubts here? Like how we calculated and how the associated primes and radical in primary decomposition are there? I mean, you know, right? This for this x cube comma y square, the radical is this. Okay. You can try this for ideal of this form x1 power a1 xn power an. Its radical is x1 comma xn. Okay, this you can check, and that's what we have used here. Okay, and let me just show you how to calculate a primary decomposition in Macaulay 2. So we know how to do how to calculate associated primes. So let us also see how to calculate primary decomposition. So our ring is XYZ. So our ring R is, let me just clear this. So my ring R is, and I is ideal. X cube, Y cube, X square, Y square, Y square, Z square. Oops, what happened? Okay, X square, Y cube. So it is x square, sorry, x cube, y cube, x square into y square, and y square into z square. So this is my ideal, and this is primary decomposition of I, not of I. Primary decomposition I. Okay. So okay, so I forgot to write this ideal here. Primary decomposition of I now is this. So did I messed up while dividing the powers, I guess? So this is primary decomposition for this ideal x cube, x square, y square, and this. So I think we calculated it wrong. So yeah. And associated primes of I is this radical of these two ideals. First one, x cube, y square is correct. The second one is only this element in associated prime, z square, x square, and y cube. We will check this. And let's see. But how do you understand how to calculate this associated prime? Let me again write some ideal. Y, and again is this. Okay, so this ideal has three associated prime, x y cube, x z comma z cube x cube, and z comma y square, and associated primes of this ideal I are these three, and this will also be a minimal prime. So see here, this is primary decomposition. So when we split them, we write them such that for each qi, radical is pi, and when qi not equal to qj, then pi not equal to pj. So we kind of merge all the primary components for which we have same associated prime. Okay, so there is something called as irreducible decomposition only defined for monomial ideals in Macaulay 2. So how to do that? So if I define I to be monomial ideal, and this is the same ideal I consider, then irreducible decomposition of I is this. Okay, so this xy is actually radical of this ideal, and this ideal here xz comma z cube x square is actually intersection of these two ideal. You can check this x cube y xz and z cube, and this last ideal z comma y square is actually this ideal here, which stays as it is. So there's difference between primary decomposition of and irreducible decomposition. So irreducible decomposition is like we are writing it as an intersection of all the irreducible elements such that we cannot further decompose it and so on. I mean, all the elements are irreducible ideal. Like if I am saying I is equal to intersection qi and qi are irreducible ideals, then each qi is irreducible ideal, and I cannot further decompose this ideal qi as an intersection of some other ideals which properly contain this ideal qi and so on. So is this clear? You can't apply this irreducible ideal definition, I mean function, to any ideal I. Okay, so if I take this ideal I and let me just all this j, and if I do irreducible decomposition of j, then it gives me error. So irreducible decomposition is a function applied only to the monomial ideals in Macaulay 2. Okay, so that's why when I declare this ideal or when I define this ideal in Macaulay 2, I have to define it as a monomial ideal. Okay, so even though the input given is a monomial ideal, but it will still give me error. So you yourself have to define J to be a monomial ideal and then try to find its irreducible decomposition, and then you will get the required output in Macaulay 2. Is this clear? How to calculate and the difference between just ideal and monomial ideal in Macaulay 2, and the difference between primary decomposition and irreducible decomposition. Okay, clear. Oh, great. So we will move back to, can you please repeat the difference? So difference between irreducible so primary decomposition is intersection of primary ideals. Okay, so primary ideal can be intersection of, primary ideals can be very well be intersection of two ideals. So primary ideal need not imply the ideal is irreducible. For example, if I take this ideal xz comma xz cube x cube, it has only one associated prime, x comma z. Okay, so let me just write here ideal x star z x cube comma z cube and associated primes of this OO. So OO means the output of previous command in Macaulay 2. So I'm writing OO means it is taking ideal x, z, x cube, z cube as its input. Okay. It contains only one associated prime. So this is primary ideal. But this is irreducible ideal because I can write it as intersection of these two ideals, x z cube and x cube z. Okay, so let me just write it. Intersect ideal x comma z cube comma ideal. So intersect is a command in Macaulay 2, using which you can intersect ideals z comma x cube, and I will check whether this is equal to I mean the equal to is check to check the equality in Macaulay 2. This my ideal this. Let me just copy it here. And it's true. So this ideal is intersection of these two ideal xz comma x cube comma z cube is intersection of ideal x comma z cube and z comma x cube. So this is primary ideal. So primary decomposition clubs all the primary components which has same associated prime. So when I gave command as a primary decomposition of this monomial ideal, it gave me this primary decomposition where each ideal is primary ideal, but they are not irreducible ideals. But when I did this irreducible decomposition, so the components of that intersection are irreducible ideals, which cannot be further written as intersection of two ideals which are properly contained, which properly contain those ideals. Is it clear, like what I'm trying to say? So primary decomposition is a decomposition of primary ideals. Irreducible decomposition is a, primary decomposition is a decomposition where components are primary ideal, and irreducible decomposition is a decomposition where components are irreducible ideals. So that is the difference. The difference between primary ideal and irreducible ideal. So this is primary ideal, but it is also not irreducible ideal, and so on. So I hope this is clear, and I can stop sharing. And you can experiment with this irreducible decomposition, primary decomposition, and associated primes in Macaulay 2 with different ideals. And primary decomposition can also be, obtained for non-monomial ideals. You can also try to find that. So I guess this much is okay for now. We'll go back. Okay, so we are back here. So is this clear? Primary component, irreducible decomposition, primary decomposition, and so on. And if you have any doubt, please feel free to ask. Otherwise, I will move to this next question. And here I think there was some problem. X square becomes x cube. That's okay. I don't know what I missed here, but it only has one primary component. Okay, it does not have two. So there is some error here. I am highlighting it. You can check this. Okay. Second component is x cube. Oh, this one here. Okay, so please check. There is some error here. Or if even if not a error, please check this. If there are any error, please feel free to let me know. Oh, yes, I guess I made a mistake here. See, here it is this is y square, and that's why this becomes y square here, and this is x cube y square z square, x cube y square z square, and that's why this is the only p primary component here, x cube y square z square. Is this okay now? Here I had written z square instead of y square, and that's why this z square remains still, but and here it is x cube this becomes x square, and intersection of these two is actually this ideal, only this ideal. Okay, because this ideal is completely contains this ideal. So this is the primary component. Let me just bring it down. This is okay. Now this Q2, if I write this Q1, Q2, Q3, this contains this ideal. So intersection becomes x cube, y square, z square. X square. Oh, there is some error. Okay, please check. I don't want to waste time calculating this, but please check there is some error here and try to solve. Because if I am writing this, this actually contains this ideal now, and that doesn't make, but it has to be x square, y cube, and z square. Just so you know. Now we will move to question 9. We can always calculate radical of primary components to find the associated prime. Yes, we can. Yes. So once we have primary decomposition, calculate its radical, and we get associated prime. Yes, you can do that. I mean, even that ideal xz comma x cube comma z cube, you can take a radical of that ideal and check what that radical is. I mean, I should have. So if I share screen again, I will do that. But first we will do that and then move ahead. But for now, let us try to solve this. Let this r comma m be. So if you want to know, this is the code for Macaulay 2, where this I is ideal. So next question, that Rm be a Noetherian local ring, and M is finitely generated R module. So we have to check this true or false, that if every element of M is a zero divisor on M, we'll see what this means. Then there exists an injective R module homomorphism R mod M to M. Okay, so in short, they are saying this R mod M to M is injection, in injective map as R module. Okay, so since M, so what does this mean is that first understand that Rm is local ring, so it has only one maximal ideal, this M given, and M is finitely generated. So M is finitely generated. This implies that M is, I'm just writing this here. Let us take F1 to Fm maybe. Okay, and what does this mean? It is summation Ri Fi. Yes, yes, this is true. This is actually true. Such that R to R. Okay, so this is finally generated, and also we have this theorem in notes you can check that if f is finite, if m is finitely generated, this implies that associated prime of m is finite set. I mean, there are finitely many associated primes of m. Okay, so that is associated primes of m over R is finite set, some p1 to pm, let us say. Okay, and we also have this result from the notes again, that zero divisors of m, that zeros of m, so zero divisor of m is, let me write this, all those are in R in R such that R into m is 0 for some m in m. Okay, so this m, every element of m is a zero divisor. So it means every element of m annihilates some element of my module m. Okay, and so, and Zm is set of all the annihilators or all the zero divisors from M. So definitely this M contains here, right? Because there might be some element outside this maximal ideal M which annihilates some element X from, let me write X here, X from my X of my module M. Okay, and we also know that this zero divisor is actually union of all these pi, where pi is associated prime of my module M. Okay, and since we know that set of associated prime is finite, we can write this as pi I from 1 to M. Okay, because these are the only associated primes M has. Any doubts here what we did so far? So M is finitely generated over Noetherian local ring. So this happens only for Noetherian ring R. Okay, M is finitely generated over Noetherian ring R. This implies associated of M is finite set. And zero divisors of M is collection of all the zero divisors. And given information is that ideal M contains zero divisors. I mean, every element of ideal M is a zero divisor. So zero divisor of M is bigger set than this ideal M given. And but this zero divisor, the set of zero divisors is actually a union of all associated primes. And this is this because there are finitely many associated primes for the given module M. So we have this prime avoidance lemma that let P1 to Pn be prime ideals and let I be an ideal such that I is contained in union I from 1 to n Pi. Then this I is contained in Pi for some I. Okay. So what can we say then? So we have this M contained in union of prime ideals. And here by prime avoidance lemma, when ideal I is contained in union of prime ideal, then that I is actually contained in one of those prime ideal. Okay, so this therefore, since, yes, exactly. J for some J, right? J in or someone less than equal to J, or let me write this. J in 1 to M. So, but M is maximal ideal. So this imply M is Pj. But Pj is what? Pj is in associated prime of M over this R. This imply this M is annihilator for some X, right? Is this clear? Just the definition. So, and now we have to define this map from R mod M to M. How can we define it? We can use this X. Okay, so we define this map phi from R to M. Okay, such that alpha going to alpha X. Then kernel of this phi is M, right? Because this is annihilator of, this is actually all those Rx such that, sorry, R in R such that Rx is 0, but that is what? Annihilator of Rx. Actually, yeah, this is kernel phi is this, which is this. Okay, so it is clear so far. So now we can define this idea, this map phi tilde from R quotiented by this M to capital M, such that now this alpha bar goes to alpha X. And note that this map is well defined, because if f of alpha is if alpha is equal to beta, then we have to check whether f of alpha is f of beta or not. But if alpha bar is equal to beta bar, this implies that alpha minus beta belongs to M. So this implies that this f of alpha minus beta is alpha minus beta x, which is 0. So this implies this f of alpha bar I hope I is sorry is f of beta bar. I hope this is clear. This implies how to, so which is 0 anyway here, and f of 0 will be 0 into x, which is 0. I mean, this is not the ideal way, but I hope you get the idea, like what I'm trying to do here, because since alpha minus beta is in M and so on. So you can check that this map is well defined, and kernel of this map check if required. And we actually checked it, but write it down properly with all the required notations. And so kernel of phi is what? This is a bar such that a into x is 0. Okay. So what does this mean? That this is all those a bars such that a belongs to annihilator of x over R. So this is all those a bars such that a belongs to M, because annihilator of x is M. So this is what? This is M mod M, right? So which is this ideal 0 in R mod M. Okay. So therefore this kernel of phi tilde is injective map. Therefore, sorry. Phi tilde is an injective map. Therefore, R mod M to M has injective homomorphism. That's what we wanted to prove. Okay, so this statement is actually true. Injective homomorphism. And this here, let us check this quickly. This, what we have to check is to check alpha bar into beta bar is equal to f of alpha is equal to f of beta. This is what we need to check in order to see. So f of alpha bar minus f of beta bar is what? F of alpha bar minus beta bar, right? And once, so this imply, so this is what? Alpha x minus beta x. Okay, from the definition. And which is what? Alpha minus beta x. But once I have alpha minus beta x, this imply that since alpha bar is equal to beta bar, this implies alpha minus beta belongs to M. So, but M is what? Any letter of X. This imply this f of alpha bar minus f of beta bar, this is the checking we are doing, is what? Some element of M into X. But this becomes what? 0, right? In M. So, this implies this f of alpha bar is equal to f of beta bar. So, therefore, well defined. Any doubts here? The well definedness. So let me just quickly go through everything again. So this much is fine, that M is contained in a set of all zero divisors of M, which is union of associated prime. But since they are finitely many, this is union of finitely, M is contained in union of finitely many associated primes or just prime ideals in general. So prime avoidance lemma says, so here we use this. So prime avoidance lemma works only for finite collection of prime ideals. Okay, we can't talk about infinite many. So if I contained in, so we can't talk anything about this. I from 1 to infinity or some I in I, pi. Then we can't talk anything about I is contained in one of the pi. This is not true. Okay, when we are in, when we can only talk about this when we have finite collection of primes. Okay, for example, you can work in this. Let me just write this. For example, this ideal x1 to xn, sorry, this ideal in infinitely many variables is contained in I from 1 to infinity is very wrong way to write it, but all these ideals of this form xi. Okay, but none of them properly contains this. Okay, so that infinite, so this does not work with infinite collection. So that's why we needed this, that M is an Noetherian local ring and finitely generated. So once we have this Noetherian ring and so on, we have this prime avoidance lemma. And because of this M being finitely generated over Noetherian ring, it has finitely many associated primes and so on. So I hope you understand what I'm trying to say here. So we actually indeed use the given facts and M is contained in some pj for some using prime avoidance lemma, and that's why this M becomes one associated primes, because M is maximal, and maximal content in some prime some ideal implies that M is equal to that ideal. And so M is some annihilator of this X. So using this X, we define this map P till phi, and this M is indeed kernel of this map P, and then phi tilde we define by R mod M to this module M, alpha bar going to alpha X. And this map is well defined. We need to check well definedness here because the domain is a quotient ring. Okay, the elements are not usual elements, but they are what I can say equivalence classes with respect to this alpha, with respect to this quotient ideal M. Okay, so that's why we need to check the well-definedness in this case, and we saw that it is indeed a well-defined map. And then kernel of this phi tilde is actually M quotiented by M. Okay, so which is zero ideal in R mod M. So therefore, this phi tilde becomes injective map, and that's why we have this injective homomorphism from R mod M to this given module M. Is it clear now? Any doubts? Please let me know. Okay. Or is this like completely? I hope I'm still audible, visible, and you all can hear me, and what I'm saying is understandable. Okay, okay, so it's true. Uh, so this statement was true, and we could actually give the homomorphism from injective homomorphism from R mod M to M. So let us move to this next question. So let P be a prime number and E be an integer, positive integer, to show that this Z ideal P power E is irreducible. And how to check this? So we have to prove this, that this Z ideal P power E is irreducible. What irreducible implies? That it is not contained in, I mean, it cannot be written as intersection of two ideals which properly contain this ideal P power E. So can you guess? I mean, what is the guess? I mean, how to start? P is prime, and this is power of prime by contradiction. Correct. So suppose P power E is equal to I intersection J with P power E contained in I and P power E contained in J properly. Okay. So P power E is, so, and this I and J are ideals of, so I and J are ideals in Z. This implies, and Z is PID, so this implies I is some X and J is some Y for this X comma Y in Z. Okay, and since this P power E is contained in I, this implies, so since P power E is contained in this I, proper containment is okay, but it is contained in I, sorry, contained in this ideal generated by X, which was I. This imply P power E divides X. This imply I can write this X as some P power, maybe K, okay, into some X dash, where GCD of X comma this x dash and p is 1. Okay, please understand this. For example, here I can have this p power e to be what I can say. I mean, I'm just giving numbers here. 3 and x could be some maybe 18. So I can write this 18 as 3 power 2 into 2. Okay, so this is what I'm like splitting this x such that GCD of 3 and 2 is 1. Okay, so this power here, it might increase when I try to write this x in this form. That's why I'm not writing this e here, but k. I hope you understand what I'm trying to do here. Okay, so similarly, I can do that. I can have since p power e, similar to I'm doing this same with y, and I can again write y as p power some, let us say L resembles, so this L, okay, L and into y dash, where again GCD of this y dash and p is 1. Okay, so but p power e is what? Is intersection of x and y, and we are in Z, so we have all those information about how intersection of two ideals is obtained and so on. So when I have intersection of two ideals in Z, it is actually generated by LCM of those, right? We know this. In Z, intersection of M is actually generated by LCM of M comma N. Okay, you can check this. So what is LCM of LCM? Let me write here explicitly. LCM of X is my P power K X dash, comma, P power L Y dash. So LCM will be P into minimum of K comma L, right? Into LCM of X comma X dash comma Y dash, because GCD of this XP and XY are 1. Okay, so that's why we can split this. So if I have some common multiples in X and Y, that multiplied by this P power minimum of K and L will be becomes the power of P in this. So this is because since P does not divide LCM of X and Y, as P does not, sorry, X dash Y dash, X dash and Y dash. Okay, so but P power E is exactly equal to, I mean, is equal to this, right? I mean, that's what we have here. Minimum of K comma L comma LCM of X dash comma Y dash. And so this implies that LCM of this K comma L becomes E. This, oh, not M, minimum of K comma L is E implies that K is E or L is E, right? Because we have only two elements. And along with this, that this LCM of X dash comma Y dash is actually 1. So this implies, because this P power E is essentially equal to P power minimum of K comma L and LCM of X dash comma Y dash. So in Z, we can say two ideals are equal when they are generated by same element. I mean, same element or plus or minus of that element. But since we are considering everything to be positive, or you can just add here plus or minus, that doesn't change anything here, because P power E will still will be equal to p power minimum of kl, and that will give me either k is e or l is e, and this LCM of x dash y dash will become my will become 1, and this will give me x and y are units. X dash and y dash are units, in fact. So this imply that p power e. So once I have x dash and y dash are units, these imply my x was p power e into one of them. I mean, if k is e, then x becomes p power e plus or minus based on whatever it is. And if or y is equal to plus or minus p power e. Okay, because this only units in z are 1 and minus 1. So this x dash is either plus minus 1 and this y dash is plus minus 1 and so on. So therefore this p power e is irreducible ideal, because the moment we had written it, I mean, even if when we try to split that ideal, it still became the same ideal. So is this clear? Any doubts here? How we did it, or how, or after this, I mean, this, and then how we got this, I mean, this section. Please see this and let me know if, okay. So it's, please explain last two steps. Okay. So what actually we did was, here this p power e is equal to this thing. Ideal m is equal to ideal n. So maximum can happen is m is equal to plus or minus n. This is clear. And let us just forget about this plus or minus. We have this in Z, ideal are principal ideals, therefore they are generated by some integers. And when I'm saying these two ideals are equal, they have to be generated by the same element. Okay, forget about the plus or minus part. Okay, I'm just talking about the positive. Suppose my Z, all the ideals are Z are generated by positive integers. I mean, that takes care of all the ideals. Okay, so p power e is p power minimum of kl and into LCM. Okay, but note that p does not divide, I mean, GCD of p and x dash and GCD of p and y dash is 1. So this implies that this p does not divide this thing. So this LCM of this x dash y dash in this product has to be 1. So if I write some x, this prime p is equal to p1, p2, p3, p4, this, okay, and if p is equal to p1, then this whatever remaining term is, this has to be plus or minus 1. I mean, in fact, plus 1, since we are, I mean, this has to be 1. Please understand this. And and this here is the only power of p. I mean, look at it as primary decomposition and we are comparing powers. Okay, and so p power e is p power minimum of k comma l. So minimum of k comma l is e. So minimum of two numbers is some e, then one of them has to be that number. So either k is e or l is e. The moment I have k is equal to e and this LCM 1, because that's the expression of x here, right? X is this p power k into x dash and y is p power l into y dash. So x dash and y dash are units because LCM of x dash and y dash is 1. So x dash y dash is unit. Then this ideal x becomes this p power e into x dash, or y becomes p power e into y dash. So it implies either x is p power e or y is p power e, which contradicts the fact that we started with p power e is properly contained in I and p power e is properly contained in j. Okay, so this is the contradiction, because this then imply that p power e is equal to I or p power e is equal to j. Okay, so that's why p power e is irreducible ideal, because we obtained this contradiction here. Oh, I did not explicitly wrote the contradiction, because this being unit actually give me x is equal to p power e into, this. Is this clear now? Because this I was ideal generated by x, this j was ideal generated by y. Now is this clear, Divya? We are just comparing these two. Okay. So this what this actually gives me, that powers of ideals generated by powers of prime numbers in Z gives us irreducible ideal. Okay, and one quick follow-up question to this is this. I want to quickly mention, it will take a few minutes, but let me show that if n is p1 power e1, it follows quickly from what we just did with pi's are distinct prime. Distinct for every I not equal to j. Then and ei are distinct for every I, and ei are positive integers. For every I. So show that this ideal generated by n is actually p1 power e1 intersection pn power en. Sorry, pr power er is an irreducible decomposition of ideal n. And can you see this? So this n, we have to show that this n is actually this. Okay, but they have said that this n is equal to p1 power e1 intersection pr power er, right? We are starting, if we start with this, the intersection is LCM of all this. PR power ER. Which is what? Since PIs are all distinct, LCM of them becomes the product of all the elements, because LCM of each two, since all PIs are distinct, this becomes, in fact, ideal generated by n. P1 power E1 multiplied by PR power ER. This is ideal generated by n. And each P1 power PI power EI is irreducible in Z as proved in question 10. Okay, so therefore this actually becomes primary decomposition of ideal in Z. So The prime factorization of Z gives us primary decomposition of ideal in Z. So is this clear? Each of this element is, we can write n as intersection of this ideal, and each of this is irreducible ideal. So that's why this is irreducible decomposition of n in Z. Okay. Any doubts here? Since these PIs are irreducible ideals as we proved here, that's why we can write this. Okay. Mm. And this is also primary. These are also primary ideals in Z, because radical of each of these is just one PI which is prime in Z. Okay, so these are irreducible and primary decomposition of some ideal in N. Is this clear? Any doubts? If there are no doubts, then we can stop, since we are anyway above 5 now. So I hope this is clear, and if there are no doubts, then we can stop here. No doubts. Okay, great. So then we will stop for today, and we will meet at the same time next week, Saturday. Okay, thank you.